In this video, we're going to go over example 11.8 in our textbook, and that video is that example is on maintaining air conditioners. So we start with going through this problem is presented to us in the four-step process method. So the first part of that process is state. So they're saying the time and hours that a technician requires to perform preventative maintenance on an air conditioning unit is governed by the exponential distribution whose density curve appears in figure 11.5a below. So this figure here is the actual population distribution of the time that it takes to perform preventative maintenance. And it's time and hours. So you can see most of them, preventative maintenance takes very little time. There are a few cases, as there are less and less cases as we get into more and more time. So don't worry about the fact that it's called an exponential distribution. It does arise in many engineering and industrial problems, such as time until failure of a machine or time until a success. But, this is just, look at this as just a regular population distribution of what's actually happening. So the mean time to repair is mu equals 1 hour, and the standard deviation also is mu equals 1 hour. So that we're used to the fact that standard deviation, we can go 3 standard deviations to either side of the mean, but that's really only in a symmetrical, nice bell-shaped distribution. In this case, 1 standard deviation below the mean brings us down to 0 hours. So you'll see almost all of the data is right here between 0 and 1. So to continue with the problem, our company has a contract to maintain 70 of these units in an apartment building, and we have to schedule technicians' time for a visit to this building. Is it safe to budget an average of 1.1 hours for each unit, or should we budget an average of 1.25 hours per unit? So we know that the average time to repair is 1 hour for all air conditioners that exist in the world, but we also know that there's fluctuation of up to an hour. 68% of all air conditioners are going to be repaired between 0 and 2 hours, which means there are a percentage of air conditioners that are going to take more than 2 hours to repair. So we've got to figure out a nice safe average time to budget. So we're going to go through the process of figuring out what is the chances that it's going to take 1.1 hours, and what is the chance it's going to take 1.25 hours before we make our decision. So to kind of go over and put into sort of symbolic terms the information that we have, we've been told that this isn't quite normally distributed, so I guess this n is not really accurate to put here. But just to present our information, our population distribution is defined by mu and sigma, which in this case is 1 and 1. So now we're going to talk about our plan. So we believe that the manufacturing and distribution process associated with the type of air conditioning unit is such that from, the variation from one unit to the next is random. So we don't know anything about the process of manufacturing, so we're going to assume that sort of the quality of one air conditioner to another is completely random. Therefore, we're going to treat these 70 air conditioners as a simple random sample from all units of this type. So what that means is we're going to assume that those 70 air conditioners kind of fall in a standard normal distribution, on a normal distribution. So that is going to help us as we go to answer this question: what is the probability that the average maintenance time for 70 units exceeds 1.1 hours and also 1.25 hours? So the way that we're going to do that is we've talked about if we have our population mean. For now, what we're going to do is assume that our sampling distribution mean is also going to have the same exact mean. So if the mean for our population in this case is 1, we're going to assume that the mean for the sampling distribution is also going to have a 1. Now we've also learned that there is a relationship between the standard deviation of the population distribution and the standard deviation of the sampling distribution of the sample means. And that relationship is that if we take the standard deviation of the population and divide it by the square root of the number of items in our sample, that's going to give us the standard deviation for the sample. So in this case we have 70 units. Our standard deviation for the population is 1. So 1 divided by the square root of 70 gives us 0.12 hours. Therefore, the distribution of our sample mean is approximately normal with a mean of 1 and a standard deviation of 0.12. And we're going to talk about the normal curve picture here. But before we do that, we'll just put this data up here at the top so that we have it to refer to. So this graph here is just talking about what we're doing here again is statistical estimation. So we're assuming that there is going to be that the density curve for the sampling distribution is perfectly normal. That's not exactly true. So they're just showing here that the actual curve is going to be slightly off from what we're working with, but we're again working with estimation, so we're going to go with the fact that it's approximately normal, which is going to help us out with our calculations. So if the distribution of x bar is approximately normal with a mean of 1 and a standard deviation of 0.12, we saw the normal curve. Using that normal distribution, we can start to calculate these probabilities. So we want to find out the probability that x bar is greater than 1.10 hours and also 1.25 hours. So these are, we can treat these as values, but they're obviously not standardized values. If we want to be able to use our standard normal table to come up with these percentages, first we have to standardize these. So let's walk through the process with the 1.10 hours. So we want to find the probability that x bar is greater than 1.10 hours. So the first thing we're going to do is standardize the 1.10. So we have our observation value minus 1, which is the mean, divided by 0.12, which is the standard deviation. So our standardized value for 1.10 hours is 0.83. So now the next thing we need to do is we're trying to calculate what is the probability that z is greater than 0.83. Now remember, our standard normal table, table A, gives us values below. When we look up a number there, it's giving us the probability that the value falls below that. And we're looking for above. So we're going to use the knowledge that the area under the whole curve is 100% or 1. And we know that to find a value above, we can subtract the below from 1. So we're going to do 1 minus the probability that z is below 0.83. So at that point then we can go to our table A and look up 0.83, and we get a value of 0.7967. We subtract that from 1 and we get 0.2033. So this is very similar to what we just did with the z-scores back in chapter 3. We're applying that same methodology to these new problems, but we're going to be using them just in a slightly different way. We're looking at the probability of means being in a certain area in these sampling distributions. So without going through the same calculations for the 1.25, what we can conclude, writing this up again in the context of the problem, that if we budget 1.1 hours per unit, there is a 20% chance that the technician will not complete the work in the building within that budgeted time. So there was a 20% chance that it's going to take longer than 1.1 hours. However, when we do the calculation for 1.25 hours, we find that that chance drops down to 2%. So there's only a 2% chance that the work is going to not be able to be completed in 1.25 hours. Therefore, it probably makes more sense for your business to budget the 1.25 hours per unit.